Alright, so this is the module 11. This is not going to be on you guys' test on Wednesday. So it's the 8 through 10 that y'all are focused on for Wednesday. This gets us into IP addressing so we can have a better understanding of how IPv4 works and how to address a network. So here's some of the objectives. Describe the structure of IPv4 address. Be able to identify the network portion versus the host portion. Understand what a subnet mask is and how it's used in relation to an IP address. We're going to compare characteristics of both unicast, broadcast, and multicast traffic. Understand public versus private. And then how to subnet these addresses. So here's the basic structure of an address. So an address is 32-bit. We know there are 4 octets, all right, because each number separated by a period is actually 8 bits. We know how to calculate the decimal value and move it into binary, or we should. So if I gave you a binary number with 8 bits, you'd be able to tell me what the decimal representation is. Here's the binary, here's the decimal. The reason we need to know this is because our router gets a packet and it opens up an address and it determines what network it's on. The only thing the router is concerned with is the network portion, which in this example you can see is 192.168.10. It doesn't care anything about the host part. Now the host part is important in the end game. Okay, so when we have 2 machines communicating with one another, to determine that it's for me, I have to look and see that the IP address, the destination IP address, if I'm receiving the packet, has my address. So that number needs to match. So when determining the network portion versus the host, we must look at this 32-bit stream, and the subnet mask is what we're going to use to determine what network we are. So for example, there's 2 portions. So given an IP address, how would we get the network portion? So I don't know if you notice here, but in the subnet mask, we have all 1s in these first 3 octets, which matches up with the network portion. Versus we have all 0s in the subnet mask, which matches up to our host portion. It's going to get trickier when we get a little deeper into this, but if you look right here, you can see if we have all 1s in the subnet mask, anywhere you have a 1 is identifying what we call a network bit, which identifies the network address. Anywhere you have a 0 in the subnet mask, this bottom portion, is identifying a host bit, which identifies the host portion of the address. So just make sure y'all heard me. So I'm going to repeat it. In the subnet mask, where you have the 1s, identifies network bits, which are tied to the network address. Where we have 0s in the subnet mask, identifies host bits, which identifies the host address. We use a process called ANDing to make the network address fall out. Now, we don't do this, but the routers do. So when they're pulling up the destination address and we're trying to figure out what the network portion is, it ANDs the subnet mask to the destination address, and what falls out is the actual network address. So AND means both have to be true. So if we're looking at 2 values, the binary at the IP address and the binary at the subnet mask, and we're taking and ANDing these things together, not adding, don't confuse that. We're ANDing them together. How would 2 things be true? What would have to take place for these to both be true? Our values are 0 and 1, right? So what has to be true for both to be true? So if you have a 0 value, is that true or false? False. Okay. If you have a 1 value, it's true. All right. So we're with me. Now, for us to both be true, they both have to be 1. So the only time you're going to get a 1 is when both values are 1. If either value is 0 or both values are 0, our result is going to be false. That is ANDing. In an OR scenario, only one value has to be true. So the two things that computers do is AND and OR. All right, and we use a combination of AND and OR to do math. All right. So in an OR situation, if we have a 1 and a 0, it's going to be true. Only one has to be true for it to be true. So we have some false true. All right, so everybody's good with that. So both have to be 1. So if you look here, these two 1s right here that give us the 192 are going to fall down. When it's a 0 and a 1, it's going to fall down as a 0. So what's going to fall down is the 192. Over here, this 168, because we're going to, only where we have the 1s, so you can see that they're going to match up, we're going to have 168 fall down. Over here, the 10 is going to fall down. When we get over here, we put all zeros in that final subnet mask portion. And so when we have all zeros and we add to whatever you have up top, what are we going to get when we're ANDing? So all zeros to the 0, 0, 0, 1, the 10, what's going to fall out? I think I just heard it over here. 0. Okay? So the actual network address is 192.168.10.0, which is correct. That's what we wanted to have happen. It basically wipes out the host portion for us, because we're looking for the network address. When you do show IP route, when you guys are doing your router labs in a little while, you'll see the network address portion inside of that table. It shows you an interface that is going to go out, or it's got an IP address that we're going to go out, and then an address that we're trying to get to. All right, so there's something called prefix length. So when they give you this /16 or /24 or /27, they're telling you how many bits from the leftmost position going forward to the right we are using. All right, so they're showing you from the leftmost 3 1s and all zeros. And I would know that the value is going to be 224. You can actually look at the PowerPoint. They've done this for you in the last octet. 224, 240, 248, 252. There's one left that they left off the screen. $254, 7 1s, with the last bit set to 0. Because we know all 1s is 255. You guys with me? So that'll make it easier for you guys to calculate up that subnet mask value if somebody hands you this. Because I recognize that as 224. If I see 3 bits, I see 224. Somebody throws me 5 bits, I see 248. And that should match with a corresponding slide. Are you guys good so far? All right, so again, ANDing, the only time we're going to get a 1 is when we have 1 and 1 show up. And they're going to show you that subnet mask ANDed with the 10.10 is going to fall down and show us 192.168.10.0, which is the network address. The reason we need the network address is because the routers need the network address. All right. So important information. When we're dealing with the network, we're dealing with something that we can use to address a whole bunch of devices. Now they've minimize this. So this is 4 PCs connected to a switch, which we know we can get switches in 5 ports, 8 ports, 12, 16, 24. They have different combinations. We know that we can do something called half duplex now. Y'all didn't know that until now, right? To the semester. Or we can full duplex. We know we use cat wire to do Ethernet. We know that we can do things at 10 meg, 100 meg, a gig. You can actually do things at 10 gig now. Y'all know that? There's even farther. There's 20, I think there's 100 gig. So there's a lot. Most of the time when you see those greater speeds, until it becomes affordable, you'll only see them within a LAN or a classroom or a building. So they're LAN based. A lot of times the higher speeds are only used for what we call the backbone connections. So everything in the classroom will be a slower speed, but then when it goes over to another building, it will be really fast. So those things change. So, but when we talk about a LAN, we're connecting a bunch of devices, so we need to understand the IP address because that's how we communicate. And you can see that we got the /24 mask with this 10 network. Well, they want you to be able to identify certain portions. So before the end of the semester, I need you guys to be able to tell me, if I give you a network address and a subnet mask, and I say, okay, what is the first usable address? I need you guys to be able to tell me that. I also need you to be able to tell me what the last usable address is, as well as the broadcast. Those are the 3 things that you should be able to calculate. It makes it permanent. So, but we need to know what the addresses we have available to us are so that we can hand them to the devices. Yes?
Sorry, it's probably a dumb question, but how do you assign a fixed address to a printer?
The same way that you do a computer, there's a static option, so we change it from obtain or dynamic to static. So printers don't have a keyboard or mouse, right? So either you're using the scroll up, down, left, right, and the number pad on the printer to put the IP address in through their software. There's a menu. Or we find out through some combination of buttons what the address is on the printer at that moment in time. And we can put the address in our web browser. A lot of times printers have a server, and so I can go into the web server software and change the address. We can use something called IP reservations, so that I know the MAC address. Hey, every time I get a request from this MAC address, give it this IP. So I can do it. That's the way I typically do it. It's through DHCP reservations, which we'll learn next semester. And I think lastly, some of them let you use their software and cable a USB cable between your machine and the printer, and then their software will find it and let you add an address, even put it on Wi-Fi as a Wi-Fi capable printer. So those are some different ways, which is done through software in some form or fashion. Any other questions so far? All right, so how do they get this last address, first address, and broadcast? So I'm gonna draw that out for you. All right, so given this, they give you the network, and that portion of the subnet mask. So this right here tells me that this number can't change when we're talking about my network, because all ones in the subnet mask means that that's network. So this will always be true, so I don't have to know about it. All right, I'm only concerned about where I have zeros when I'm trying to calculate first address, last address, and broadcast. All right, so just so you guys know, because this is a 0 and this is all zeros, that means that this right here belongs to the host portion. So if you take the network address and you turn on all zeros in the host portion, you set all the host bits, because there's 8. This identifies 8. So if I set them to all zeros, I just created the network address. All zeros in the host field is the network address. Voila. It's magical. You guys can see it now. All right, that's not allowed to be used to assign to a printer or device on the network. It's unusable. It's the network address. So that one's gone. I think I spelled that right. Also, all ones, unusable. That creates a whole different address. What's that create? Boom, broadcast. I heard it. So if I want to broadcast to every host on the 10 network, I turn all ones on in the host field, creates a broadcast address. Boom, unusable. Cannot put that on your network devices. So if I wanted to calculate up how many addresses that I have are usable, just so you guys know, there's a formula. So you take the number of host bits, which we know is 8. So we go 2 to the 8. And you subtract 2. Because there's 2 things that we can't use. We now know the 2 things are all ones and all zeros in the host field, which gives us the network address and the broadcast address. So we have to take 2 away. 254 usable addresses when we're using a Class C or Class C subnet mask. And so everything in between, so we said we can't use 0, we can't use 255. So everything in between is usable. So in my mind, that says 1 through 254, right? Because we can go from 0 to 255 inside of an octet. So the first usable address would be? The first usable IP address would be? 192.168.10.1. And the last usable address would be? 192.168.10.254. So now can, given a subnet mask, calculate a first and last address. You with me? At least on a Class C. It'll get a little trickier when we get into a B and some other ones. But you guys are good with that, right? So remember that IP is a connectionless protocol because we're letting all the other layers handle the connections. Unicast is a one-to-one thing. So if I'm communicating from my PC to a server or from my PC to another PC and we're on the same switch network, it's going to come in from my machine to a port on the switch. It's going to be looked at the MAC address table at the switch, and then it's going to go out the corresponding destination port. And it's going to retrieve or come back on that receiving port or the sending port, and then return on the one that was initially sent in on. It's just going to go back and forth. That's unicast. It's one-to-one. Nothing else on the network sees that packet. It only flows between the port it goes in on and then the corresponding port where the device is. Everybody okay with unicast? All right. So there's some other packet types. One of those is a broadcast. So remember, if we don't know the MAC address of the device that we're trying to talk to, we have to retrieve that somehow. The way we retrieve that is with an ARP request, which is a broadcast packet. And so the machine is trying to find you. Maybe we have an IP address, but we don't have the MAC. Sends into the switch. And because the switch doesn't have the MAC address, or it doesn't know the device, or the PC doesn't know, we've got a broadcast for the person that we're trying to talk to. So it goes in on a port. It will not come back out on that port. It will come back out on every other port on the network. So if this was a 24 port switch, when it came in over here, it would have came back out on all other 23 ports. If it's a 48 port switch that came in on that port, it would come out on all other 47 ports. You with me? So broadcast, in regards to the switch, it will come in on one port and it goes out every other port. And it's going to everything on the network. You guys now know that we turn all ones on in the host build. That's the address that's going to be used for sending to broadcast on the 4 network. So this right here is a special broadcast. So y'all see this? Destination all 255s. So it's going to send to everything on the network. It's like, hey, we don't care. I'm just sending to everything. There's another form of communication that we use in regards to making contact with devices. So one of those things is multicast. All right, multicast is used by both IPv4 and IPv6. The previous broadcast that we talked about doesn't exist in IPv6. So make sure you're aware of that on this test. That is going to be a testable item on the next test Wednesday. So why does IPv6 not have the broadcast? You may want to know that.
Is it because of the thing we talked about Wednesday that I can't remember the name of? Like it doesn't do, it does something neighbors thing?
Yes, that's the ARP. You need to know that too. So IPv4, we have to find the MAC address and the IP address for communications, and we use ARP to do that with IPv4. IPv6 doesn't use ARP, it uses a different method called neighbor solicitation and advertising. Yeah. So yeah, you need to know that. So multicast, I'll just give you guys an example. So when we get into the routing protocols, we have all our Cisco routers and they're all talking about OSPF and sharing information back and forth. They do that using multicast, and there's a specific multicast address they use. Just know if you guys see something that starts 224, they've given you more than that here. If you see something that starts 224, it's a multicast address in IPv4. I think we reviewed this ahead of the slide because I wanted you guys to know what a private address is. Do y'all remember this? We talked about it. The reason we need to know this is because of the IPv4 depletion, like all these addresses are gone. And for us to make a connection from a LAN with, let's just say 200 machines to start with, out to the real internet, we have to bind all these 200 devices to a public address. If you don't have a public address, you're not allowed on the internet. Okay? We know that there's a very few of those. So typically what we do is we'll have an ISP, AT&T for example, and AT&T will provide us a public address to use, one. And so all of our machines on the inside, there's 200. So we had to come up with something called NAT, Network Address Translation, that allows us to get to the internet. Without NAT, IPv4 addresses were useless. All right. So if I wanted 200 machines to go out and for them to not have NAT in play, I'd have to have 200 public IPs. We know that there's only like 4 million. Is that right? Or is it 4 billion? I think there's 4 billion IPv4 addresses. Well, there's more than 4 billion people on the planet. We know that with IPv6, there's like undecillion addresses. I think it was like 340 undecillion. Like that number's too big for a calculator. We're not going to run out. So everybody can have one. That's not a problem. And that's why we don't have to broadcast with IPv6. It's because of the size of the address space. There wasn't as much of a need. All right. So we created these private address spaces. If you look, there's the RFC 1918. You guys can look it up, private address range. When they started seeing that they were having problems with IPv4, it's like, oh, we're going to be out of addresses. We got to keep this alive for some undefined amount of time. How are we going to do that? Oh, we'll come up with NAT and IP address and private address ranges. And here they are. So you guys are allowed to use any of these, assign them however you want. The only one that's a little tricky is the 172, all right? Because in that second octet, if it's a 16 through 31, it is a private address. If it's any other number, it is not. So 172.10 is public. That's owned by somebody. 172.16 is private. 172.18 is private. So if it's got a 16 through 31 in that second octet, so we know it's going to start 172, and then we look at that second octet. If we see 16 through 31, we know, oh, somebody's using private. So that's not something that's on the internet. It's fallen into this RFC 1918, and it can't be on the internet. None of these things are allowed on the internet. We have to NAT to a public to put it out there. So NAT has to be in play if you see these addresses. Everybody okay with that? So network address translation, private addresses to public, is typically enabled on an edge router. So they show you the edge router is the router that's connected to the ISP. So in this case, each one of those suckers is the edge. Each one of these things is running NAT. All this out here is public. So this guy's got to take the private and bind it to whatever the public is and put it out on the wire. It's not allowed out as itself. So just so you guys can see, I'm going to make up some public. You guys know you can just use Aaron, who is. To punch an IP address in and see who owns it. All right. So you can take and pop that in, and it should come back and tell you some ISP owns it. So in this example, I'm just going to draw a LAN. That they gave us before. So usually on the router interface on the inside, we use the first or the last address. Makes it easy to keep track of. Now, I every now and then will do something a little crazy. Maybe come over here and make this like a 96. Because I'm going away from the norm, it's going to make it harder to find the gateway. So if you're inside trying to get on my network and I'm not wanting you on my network, I might be able to hide and keep you off a little bit by just changing one little thing. Maybe you're not smart enough to figure it out. So, make sense? Typically, you go somewhere everybody uses the first or the last, so it's real easy to find. I'll go, okay, I'll ping this. Does it respond? Yes. I'll go, what is it? And it'll come back and go, oh, that's a router. I'm like, yeah, that's the gateway. Also, I'm on the network. You guys with me? So over here on the outside, this public address is given to you, is provided. All right. And the reason I'm pointing this out is if I get a request from inside for Google, we know that we do a DNS query, find an IP number, and send the request. So let's say that Google is, all right, which that is their DNS, but it's not their website. So we'll just say that is. When it comes up here, the router says, okay, I've got this 10.20 and it's trying to connect to all 8s. And that takes and binds this and some randomized port to you. So if you guys do a net stat, what we learned about, and we see this 53678, it's the router tracking the session. So when it gets over here to Google, Google sees you as this. When Google responds to this. They receive it on their 80. So just so you guys know, anytime you guys see a colon, they're giving you guys the associated port, which is at the transport layer. So it's the application. So it could be web, it could be Skype or VoIP. We don't know what it is, but this is an application that we're tracking a session for, right? So the number is being generated by the router, and it's the public. All right, so just to recap from last week, we started this chapter 11, IP subnetting. There are two parts to the IP address. There's a network portion, which is identified by ones in the subnet mask. And then there's a host portion. So this is the actual device address. So phone, PC, printer, whatever that device may be. Careful. Whatever that device may be is identified by the device portion of the address. The network can be related to like a street. They gave you some subnet mask prefix. So subnet mask on a class A default is a /8. Looks like this. So you can see that there's a lot more host addresses available because remember, everywhere there's a 0. Formula for the number of host addresses is 2 to the H bits minus 2. So there's 24 zeros here. So you'd have 2 to the 24 minus 2, which should be like 16 million plus addresses on a class A network or a /8. On a /16, this is the default subnet mask for a class B, 255.255.0.0. We have 16 host bits represented by the zeros. So 2 to the 16 minus 2 should be 65,000 plus addresses on a class B. Finally get down to a class C. The number of host addresses is shrunk. We have 8 zeros. So 2 to the 8 minus 2, 254 computers on every class C network. So the ones again define the network bits. The zeros define the host bits. You can see that we can actually create other subnets. So they give you the /25 through 30 options here. By borrowing or increasing the network bits, we're increasing the number of networks we have, but we reduce the host space. So you can see if we have 4 zeros, that means we have 2 to the 4 minus 2. So 2 to the 4 is 16, right? Y'all agree with that? 2 to the 3 is 8. So 2 to the 4, we only got 16 minus 2. That means 14 devices on that network. So this gets real small as far as the number of devices. The process of determining what the network address is the process of ANDing, A-N-D. So when we AND the IP address given or on our host with our subnet mask, what's going to fall out is the network address. Because everywhere you have ones, whatever is above it is going to fall out. So if it's a 1 above it, it's going to have a 1. If it has a 0, it's going to fall out as a 0. Anywhere we have zeros in the subnet mask is going to be erased. So if you have zeros in the subnet mask, anything above it is going to fall out as a 0. So it's going to basically be wiped out. So this is what they want you guys to be able to do. They want you to be able to calculate, given a subnet mask and a network number, what your start and stop is, the usable IP addresses, what's going to go on the device, and what the broadcast is. everybody okay with that so far? So you can see on this slide, they show you the subnet mask, they show you the network address, and then they show you how to calculate first, last, and the broadcast. We covered the difference between unicast and broadcast. One of the problems with IPv4 is that we have a depletion issue, so we have to run NAT. Because of the size of networks and the way IPv4 was written, we are going to have broadcast traffic. Broadcast causes congestion. So you think about it, 98 at 7:30 in the morning, it's full of broadcast traffic, right? It's hard to get up and down Highway 98 or Hardy Street first thing in the morning. As the day goes on, it gets a little bit less, so the broadcast traffic shrinks. Same way in the mornings, our networks have a lot more broadcast traffic on them than they do other times of the day. So RFC 1918. So anytime you guys see these, if you guys wanted to do more research, you guys could Google and look these RFCs up. But our RFC 19 says, hey, we have public IPv4 addresses. These are ones that are allowed on the internet. They're routable. They typically are given to ISPs or other entities that can then pass them on to smaller entities. Private addresses are common blocks used by all organizations or most organizations for their internal hosts. So because of the depletion problem, we came up with these private address numbers. So you can see that anything that starts with a 10 is a Class A and it's private. Those 10 addresses are not allowed on the internet. Anything that starts 172, 16, 17, 18, 19, all the way through 172, 31 is a Class B. It is not allowed on the internet. Those are also private. And anything that starts 192, 168 is a Class C, and it is also private, not allowed on the internet. These are not unique, and they can be used internally with any network. So as a network administrator, you guys can choose what numbers that you want to use. Obviously, Class C only supports 254 computers. So if we have a small network and it's not going to grow very big, Class C network is fine. You get outside of a small office or a home, it's not hard to use up 200 addresses. So you got to have at least a Class B. So private addresses, again, are not routable. So we have to have something called NAT to translate, to hide those private address numbers. So that's the purpose of NAT. So we use this to bind our private IPv4 to a public address. When you guys pull up your Chrome browser or your internet browser and you guys type ipchicket.com, it pulls back and shows you an address. It's not the address on your machine, it's the address that people are seeing you on the outside as. That's your public address. If you do an IP config at the command prompt on your computer, it'll come back and return your private hidden address. So two different ways to look at it. We use both. Every device in here is going to have a private address, but when it gets to the internet, it's going to have a public, and it's handled by NAT in our router. It's typically enabled on the edge router, connecting us to the ISP or the internet, and it translates the internal private addresses to public. So they talk about loopback. I think we mentioned this as well. So loopback is a internal number that we use for testing. What we're doing is we're testing our local connection. So if you guys were a web designer and you're doing websites and you wanted to test their functionality, we're probably going to run a web server on our local computer. You can take and pull up, if the web server is running and you have your website there, you can actually in your browser type 127.0.0.1 and press enter, and it should pull back the web page that you guys are working on your local machine. But you have to have all those things correct. The main goal of the 127 address is for us to test that TCP/IP is bound to our network card on the device that we're working with. So when y'all run a ping to the 127.0.0.1, the only thing it's telling you is that your device has IPv4 installed and that it is bound to the network card. Is everybody okay with that? This link local. So on IPv4, they have this 169.254 address. If you see this, it's probably not good. All right, and I'm going to tell you why. So Microsoft and others came up with this automatic private IP addressing scheme called a PIPA. So automatic private IP addressing. You see the A, the P, IP, and A make a PIPA. And the purpose of it is to assign you an address that hopefully you can communicate with other things on the LAN while we're trying to figure out what's wrong with the network. So the only time you see this is if you have your adapter set to grab an IP address dynamically, which is almost always, and it can't get it for some reason. So when DHCP fails, we can't receive an address from our server, or a server can't hand us an address, your machine will automatically bind itself with this 169 number. So if you guys ever are out in the field and you guys run up on this 169 number, you now know that means that the machine is having issues. So either the wire connection to the network is not working, or my wireless connection is not working. Whatever the reason, I can't talk to the DHCP server and it can't give me an address. So I got to figure out what's wrong with my connection. All right, so if you ever see 169, whether it be on a phone or a computer or mobile phone trying to get on Wi-Fi, if you see a 169, you guys now know that you're not getting an address for some reason. There are a bunch of classes of networks. We've reviewed this. So if you can see anything that starts, the first octet is the important one. So if it's a 0 to 127 in the first octet, it's a class A. We know that a class A has a /8 or 255.0.0.0 mask by default. Class B starts 128 in the first octet up to 191. 128 to 191. It's going to be a class B. So the first number is what you look at to determine the class. Can y'all look at the subnet mask? Who remembers the answer to that question? If I said, hey, the subnet mask is 255.255.0.0 on this network, can you tell me what the class is? So I heard one person say it's a class B. Can you determine the class of the network given the subnet mask? There's only one thing that's going to determine the class of the network is the actual network or IP address and that first octet, that number. You can't tell because, okay, the network could be 10.0.0.0 and the subnet mask could be 255.255.0.0. That's a class A because it started with 10. So the subnet mask can't be used to determine the class of the network. So don't let them trick you with that. It looks like a class B, you're right. By default, a class B is a 255.255.0.0 /16, which is what we have for this class B. But it does not determine the class. Only the number and that first octet can determine what your class is. Nobody can take it away from you. All right, so anything 192 to 223 is going to have a /24, the 255.255.255.0. And that's a class C network. The bigger the subnet mask, the smaller the number of hosts on a network, but the more networks we have. Okay? They show you this in a pie chart. So on a class A, we can have 16 million hosts on a class A network. It's a lot of hosts. You're not going to build a LAN with 16 million hosts on it because the way IPv4 works, it would be very bad. All right, classful addressing wasted many IPv4 spaces, so we got NAT. They talked about this. You guys see class D or E, you're working somewhere where there's experimental research, science, some special military, something out of the norm. You're not in enterprise, business, educational environment, most likely. All right, so those things are reserved. You don't see those very often in the real world. So the class D and E are there. They give them to you. All right, so IP addresses can also identify our origin. So you can see that there's ARIN, which you guys have learned about, where you can punch an IP address in and come back and tell you who provided that IP address or who owns it. That's tied to the American region, North America. There is a Latin. I did do that time. There's a African, there's a European with the right, and then there's an AP or Asian Pacific. Zoom back.
I don't know what you're doing. For whatever reason, it keeps highlighting over the, like on my computer itself, it keeps on selecting the zoom in tool. All right. There we go. I think I got it fixed.
All right, so broadcast domains and segmentation. So by default, one interface on a router encompassed by this yellow square makes up a broadcast domain. Every interface on a router is a different broadcast domain. So the only way to segment broadcast is with a router, which is technically true. There are also multi-layer switch devices that we can use now. There are lots of things that do broadcast. Remember, broadcast we can actually capture and see. So ARP, when we were doing the ARP study, you can see that with the Wireshark capture. ARP uses broadcast located on other devices. It sends the DHCP discover broadcast to locate the server. So DHCP uses some broadcast. DNS uses some broadcast. Switches do not block or stop broadcast from occurring. People get, or students that I've seen over time always confuse this for some reason. So switches are not going to prevent broadcast. They do microsegmentation, and they improve the way that we do send things in and out, but they do not stop broadcast. Broadcast can still occur, and it needs to occur in IPv4. Remember, when we get into IPv6, the need for the broadcast is kind of eliminated. The only device that stops broadcast is a router or a layer 3 switch. Routers, again, don't propagate, so they don't let it go from one interface to another. So it stays within the yellow domain. Switches don't shrink the size of broadcast domains unless we use something special called VLANs. All right, we'll get into it in the next semester. Let's see if we got this fixed. Nope. Put that on there. Now we're good. All right, so large broadcast domain has a lot of hosts. Excessive traffic negatively affects the performance of the network. So what we do is reduce the size of the broadcast domains. So the way to do that, one way is to add other interfaces to a router and cut things in half. So you can see they started with 401 interface. They split it into two different network numbers with two different interfaces, and they cut 400 down to 200 on each side of the router, shrinking the broadcast from 400 users to 200 users. So this is one way to resolve this. So every time you want to shrink the broadcast domain, you would add another interface to the router, add another switch, and then move some of your devices over onto the new network. So what are the ways we can group things? There's all kinds of ways to group and segment. Here they give you a multi-floor building. You can see by floor, every floor is a different network address. Over here, grouper function. So you got administration, human resources, students, accounting. So each group or function is a network. And then sometimes we do it by device type. So you got printers, servers, workstations. So the device type, function of our devices. So what does a subnet look like? How's it defined? Well, again, we talked about this earlier. Our subnet mask defines the N bits, or the network bits. The number of N bits determine the number of hosts. So when we have a class A, a /8 with a 255, we have 3 sets of zeros. Those are our host bits. You can see there's 24 bits. 2 to the 24 should come out to be 16,777,214. Of course, you lose the broadcast and the network number in the math. /16, we have 16 H bits, 65,534 devices on a /16 or a Class B network. Now, we can take and change masks. This is a process called subnetting. All right, so given an IPv4 network address, in this case they got a class A, a 10. By default it's a /8. So if we take, you can steal from host bits. You're not allowed to steal from the network bits. So by default we know the first 8 bits in a class A are used. We can't touch, they're untouchable. All right. But anything else that's an H inside of a class A can be borrowed and used to create more networks. So you take from the H bits. Now I'm going to see y'all do this. Pay attention. Don't go to the far right-hand side of an address. Over here in this example, you see where the 254 is? We're not going to go over there and borrow back towards the 10. You have to start on the other side of the 10 and work your way back towards the 254, all right, in the address. So you can see that they did a /16, and they're showing you down the road here what it looks like. So class A by default is a 255. This is a perfect example. We asked earlier, if I gave you 255.255.0.0, could you tell me what network it is? Obviously we can't, because you can see that they're using that subnet mask on a class A. Now what they did was they took this second octet, which you guys can see here, the 0, the 1, the 2, the 3, all of these numbers are now changing our network. So each one of these is a different network. It has a different start-stop IP address, and it has a different broadcast. So on a class A by default, if you remember from the screen before, we had 16 million addresses or hosts. They've taken that class A, they borrowed 8 bits from the second octet. So by doing so, they have 2 to the 8 networks. Because we can go from 0 to 255, so 2 to the 8 is 256. If you count from 0 to 255, that gives you 256 numbers. You created 256 networks, each with 65,000 addresses on them each. Because we're mimicking a class B. We know from the math that 2 to the 16 minus 2, which is the number of host bits that we have left. The last two, we have octet 3 and 4 still available for host addressing. 2 to the 16 on a class B gave us 64,000 or 65,000 addresses, right? So now we just took a single class A, turned it into 256 class A's with 65,000 addresses on them each, instead of one class A with 16 million networks. With me? All right. So on this next slide over here, they took the same class A and they did a /24. So we're borrowing 16 of the host bits. So now we have 2 to the 16 networks. So you have 65,000 class A networks. You've broken it up. And on each one, we have 254 addresses, because we only have the 4th octet left to use for making device addresses or IPs. So you can see your address scheme changes. So you got 10 to the 10.0.01 through 254, 10.0.0.255 is the broadcast port. 10.1.0 would be a different network. It would be 10.1.0.1 through 10.1.0.254 with a 10.1.0.255 broadcast. So you can change over here your network address or number by borrowing bits. So you guys can see that there is a /25 prefix. They took a class C, they borrowed 1 bit, is bolded over here. By borrowing 1 bit, you've generated 2 networks. So remember, this thing's base 2. So every time you borrow 1 bit, you're going to increase the number of networks by 2s. So if I borrow 2 bits, it's going to be 2 times 2, or 4. If I borrow 3 bits, it's going to be 2 times 2 times 2, or 8, because I borrowed 3 bits. So when you borrow, you increase the number of networks, because we're borrowing bits. The remaining host bits is going to determine the number of hosts. So when you do a borrow 1 bit from 8, that leaves us 7 bits. So 2 to the 7 minus 2 is the number of hosts per network. Should be 126. If I borrow 2 bits, my math changes to this 192. I now created 4 networks, but I also shrunk my 8 to 6. So now I got 2 to the 6 minus 2 should be, how many? 2 to the 6, 62 usable networks. Hosts, 4 networks. If you borrow 3, it's going to get an 8. Cuts the 62 in half. We're now at 30, right? Do it again. I got a 16, leaving 16, so I'm at 14 usable hosts on the 16 networks. So anytime you borrow a bit, we double the size or the number of networks, but we half the size of how many devices can go on there. Any questions so far? So y'all see what they're doing, right? So when they borrow a bit, they're flipping one of the host bits to a 1. They add the value of these 3 bits. So that's a 128 plus a 64 plus a 32, which gives them the 224. Over here on the 192, you got a 128 and a 64 bit on. We add those together, it gives us the 192. If you add 4, you're going to get a 240, so on and so forth. So they're calculating that summit mask. All right, so what they've done here is they've gone back in and they've taken a /16 or a class B, and they're doing the same thing that they did with a class C on the previous slide. So you can see where your network bits started, and then what happens when you borrow 1. So your 255, we add a 128 to it. Creates 2 networks. So on a class B, by default, remember, you have what, 65,000 addresses? So when you borrow 1 bit, it changes our bits from 16 to 15, and it should cut it in half. So we should show 32. If we double this 32, we get that number that we would get if we did 2 to the 16 if we had all of these bits to use, right? So again, as you borrow a bit, the number of networks increase, and then the number above before is going to cut in half. Borrow a bit, double the networks, cut the number before in half. So you can see there's a lot more hosts available on a Class B network. So it makes it real easy for me to increase. So if I borrow 256, which would be this whole third octet, right, giving me what looks like a Class C network. On each one, I'm going to have 254 computers. And I got 256 networks to play with. So what's going to define how you guys do this, how you subnet and you use addresses in the real world, is the number of networks you need. Okay? So if you guys go to work for McDonald's in Mississippi, and the guy that owns McDonald's has 100 stores, that's 100 networks. Right? So I know that I have to borrow at least the /23 if I had a Class B. So I could have 128 networks, at least. So that's one thing that's going to define how we borrow and create networks. The other thing is how many hosts or devices are going to be on a network. Imagine if we're talking about like a McDonald's, the number of devices on the inside of that store is going to be minimalized. So you probably got TV screens that look like TVs, which in reality they're probably computers, right? Because those boards change with ads and new menus and new products, and we flip that stuff around, and we can only do that with computers. If it's a TV screen that's not changing, right? It's fixed, then it's not going to be a computer. But I imagine that those have to have IP addresses. So if you have 3 screens, that's 3 IPs. If you have 3 terminals at the front, that's 3 more. Every credit card terminal is probably a different device, so that's 3 more, right? Printers everywhere probably have addresses. There might be 6 or 7 of those. You guys with me? But that number is small. So I would imagine with 60 or fewer addresses, we could handle something like that. So I could go way down to where maybe I borrowed all the way to the 128 where I have 512 networks and only have 126 devices on each. So you got to figure out what the math is to minimize loss and waste. Right? We're IP conservationists is what we are. We got to choose the best subnet mask and scheme that fit our model, what we're trying to accomplish. You guys see it? Is that helpful? All right. So they may ask you something like, hey, what are you going to have to do to create 100 networks? So for one, if I gave you a Class C, could you create 100 networks? How many bits do you have to play with if I gave you a Class C? Y'all answer the question. How many bits do you have to play with? How many can you borrow from if you have a Class C? Could you create 100 networks? Oh, somebody. You got a Class C network. What's the default mask for a Class C? Huh? The full mask. What's the full mask, subnet mask of a Class C network by default? Is it a /8, /16, /24? /24. Okay. So that means there's 24 bits gone. We're not allowed to touch. Those belong to the network already. So how many bits do you have to play with? How many bits total are there in an address? We're trying to borrow bits, all right? So if I gave you a Class C, you're not allowed to touch any of the ones that already exist. You just told me there's 24 ones. So how many zeros do you have? 8. All right. So the formula to create the number of networks is right here on the board, right? So every one you borrow is going to create 2, and it goes up multiples of 2. So how many do you have to borrow to get to a number that's 100 or bigger? Here, we're looking for 100 networks. So how many bits do they have to borrow to get to a number that's bigger than 100? 7, right? 2 to the 7 equals 128. All right, so you have 8 bits that you can play with, and you borrow 7. That leaves you with 1 bit. Can you have a network with 1 0? So remember, every network's got a network number and a broadcast that we lose. And if I have 1 bit, that's a network number and a broadcast. Do we have anything else on that network? No. So you can't use a class C to solve this problem. It has to at least be a class B. Because a class B, you start with a /16, and we have 16 bits to play with, so we can borrow 7 bits and be good. You see where they're going with this with the math? So if I borrow 7 bits from 16 that I have on a class B, how many do you have left? So on a class B, you got 16 to play with. If you borrow 7, how many do you have left? 9. All right, so how many computers do you have if you have 9 bits left? If I borrow 7, I know that I've created 128 networks. I have 9 left. The only thing that changes in the formula is we take 2 away from it. So 2 to the 9 is what?
512.
Okay, 512 minus 2, so there are 510 computers on every one of those 128 networks that you create. If you borrow 8 bits, leaving us 8 bits, I just created 256 networks with 254 hosts on each network. You basically turn a class B into a class C. So you can use this to do a little bit of math. You could borrow 7, you could borrow 8, you could borrow 9. All of these meet the requirement of 100 networks. I can't borrow 6 because that's only 64 networks. It's too small. It's not meeting the requirement of 100 networks. Y'all with me? They didn't say how many hosts you have to have. So we're not limited. I can borrow any number as long as it gets me above 100. All of those would be correct answers. Okay? I would want more information. All right? I would be like, okay, I'm going to create you 100 networks, but how many devices are you going to have on each one of these? Because I know how that works. I want to make sure I got enough addresses to use on the networks that we create. So sometimes the math gets bigger. I need to have 1,000 networks. Okay. So how would I do that? You can see I got to borrow at least 10. So the number of bits you have to borrow increases. Could I do this with a class B? Sure. But just know when I do, I only have how many bits left for hosts? If I borrow 10 on a class B? So you got 16 bits on a class B to play with. If you borrow 10, how many's left? 6. 2 to the 6 is what? 64. Okay? So you got 64 minus 2, 62 computers on each network. As long as that's enough device addresses, you can use a class B. If the requirement was 1,000 networks and 200 hosts on each network, class B no longer helps me. I can't use it. I'd have to go to an A. Start with a 10. So this right here, given a private address, meet these requirements, allows you to choose whether I use a 10 a 172.16 or 192.168. You're in charge. You're the administrators. I've gotten to that age now. I go, hey, this is what I need. Go take care of this. All right? Because I've showed you, taught you, you guys should be able to do this now. Y'all with me? So if you have an A, we're at /8 by default. We have 24 bits we can borrow from. A lot more hosts, a lot more networks. You can do more with it. So subnet to meet requirements. So an internet company internal network uses private IPv4, a DMZ internet facing servers with public addresses. You could use a 10 with 8 on the 16 or 24 boundary. The DMZ devices would have to be configured with public addresses. That's not necessarily true. So out here, you guys could have public addresses on devices if you wanted to put them in a one-to-one situation. We can put private and have a different network out here and do something called PAT to translate stuff onto the inside. Do it all the time. So these things here, if they have the potential to be broke into and cause us problems, they put them outside the network on something called a DMZ. But this would be a separate network, separate interface. A lot of boxes now have something called a DMZ. On the routers in the lab, this would just be a different gigabit interface. And then over here, you have your internal LAN or LANs. So planning is based off those two things that me and you have been talking about, the number of networks we need and the number of hosts on each network. Those are the things that are going to determine the subnet scheme that you use and the private address scheme that you choose. So you can see they give you guys different examples with public versus private addresses. And then that brings us to this new topic called DLSM. I'm going to pause here because this is where I got to this morning. I'm going to go ahead and link the video that I created earlier because Josie's going to take this one and manipulate it. Let me real quick on the board, how much time we got left? 30 minutes. I'm going to go through the subnetting on here so you guys can see it. You're going to clip and edit this stuff out, right? And I'm going to share Excel that I created this morning so you guys can use Excel to manipulate this. So they may give you a zero address, and then they'll tell you, hey, I want 100 networks with, let's say, at least 120 hosts on each. So they call them subnets. A subnet is the same as a network. It's just a broken up piece of it. We know by default that this is a /16, and the mask looks like this. See my other pins better. Okay. So if we're trying to figure out how to do 100 networks, this section right here, where you have zeros, is our host bits. Our host bits is where we're allowed to play. You guys saw from the slide that 2 to the n, has got to be greater than or equal to 100. That's the number of bits I need to borrow to get 100 networks. You guys with me? All right. So in this situation, if we did 2 to the 6, is this true? Is 2 to the 6 bigger than 100? Because 2 to the 6 is 64, right? This is not true. So we can't use 6. 2 to the 7, we know things double is equal to 128. It is greater than or equal to 100. We know that we have a class B, all right? So we have 16 bits. I just took 7 away. That leaves me with 9, right? So minus 7 equals 9. So this right here, 120 hosts per net, would be 2 to the 8, which is equal to 9. Is it, and we subtract 2, is it greater than or equal to 120? Well, I know 7's bigger than 128. If I do 8, that's double that. That's 256. 9's double that. So this is going to be 510. Greater than or equal to 120? The answer is yes. So that works, right? So you guys saw you can calculate this up. So what you've done is you've changed this mask. So we know we need to borrow 7 bits. Trying. So the values don't change. On the other side of the period, we got a 128, a 64, a 32, a 16, an 8, a 4, a 2, and a 1. That's 2 to the 7 on down to 2 to the 0. So 1, 2, 3, 4, 5, 6, 7. That's going to be a 0. Everything else is going to be a 0. Guys with me? So this creates our new summit mask that we're going to use on all our networks, because we said we want to borrow 7 bits because 2 to the 7 was greater than or equal to 100. So there's your 7 bits you just borrowed. So if you add these up, what do we get? You did? How'd you get that?
You added everything but that last 0.
Yep. So we know all 1s is 255. We know the value of that's 1. So 255 minus 1 gives us 254. So you nailed it. So that's going to be the same on every one of these networks you just created. So we just changed this default mask. All right, so this was our starting network right here. So just so you guys can see it, what you've done is you said, okay, I can take 1, 2, 3, 4, 5, 6, 7. I'm going to draw a line. We still have a 8-bit over here, and we have all these 8 bits. Okay? So on this side of the line, these belong to the network. So anytime a bit changes on the network side, we're on a different street. Run a different network. You guys with me? Right. So this is every interface of the router gets a different network, a different street. Yes?
So when you're on the network, everything that's going to be through, everything that's going to the subnet mask is going to be a part of your range.
So everything over here is going to be a part of the range you can use, yes.
Okay.
Y'all with me? So this defines our network, our broadcast, and usable addresses. The host bits, the stuff that you left alone. So every one of these became an N when I defined it with a new mask. Everything over here was an H. Because I left them, I didn't touch them. This is still a 0 or 1. This is still a 128. That's defined by the periods. Okay? So, all zeros is a network. That is a different network. By changing that 1. So they borrowed to the 2-bit, just so you guys know. That's a 128. So this is referred to as a magic number inside of the chapter in the slide. Where you guys borrowed to is how your networks are going to increase. So 0 and 1, sorry, yeah. 0 all the way to 2, so 0 and 1 are on the 0 network in this example. When we move to here, I'm on a different network, it's 2. The next network would be 4. The next network would be 6. The next network would be 8. You with me? Because we're going up by 2s because that's where we borrowed to. If I'd have borrowed to the 4, the magic number would be 4 if I'd have borrowed to here. So 0 would have been the first network, 4 would be the next one, 8 would be the next one, 12 would be the next one. You guys with me? The number of hosts increase. All right, so to determine the network number, you write your network number, set the bits the way you want them, and then put all zeros in the host field. So the network number here is 172.16.0.0. You with me? So I take and I flip this one. 128, 64, 32, 16, 8, 4, and 2. Flip this on. You put all zeros in the host field. Our network number is going to be, just like we discussed, because we're going up by 2s. The next number, or next network would be 3, 4. You put all zeros.
We just died.
It's fine. You got a new network, which should be 4, right? Because we're going up by 2s. Y'all buy that? If you want to find the broadcast address, you take the network number that you're working with, and you flip all these to 1s. So 8 1s is 255. Plus 1, right? Because that's a period right here. We know the value of this is 1. Plus all zeros is 1, right? So this number, you notice, is less than the network number below it. It's not 0. This is on the 0 network because these bits did not change. So as long as your network bits don't change, you're on the same network or the same street. Just like when you're driving, right? If we're on Hardy Street and I ain't turning left or right, I'm still on Hardy Street if I'm going straight. Y'all buy that? So everything in between all zeros and all ones is a usable IP address. Everything between the zeros and ones is an IP address. So if you had to write the range would be 172.16.0.1 through kind of weird looking. So 0.1, 0.2, 0.3, 0.4, all the way to 0.255. So don't get confused by that 255 thing.